Okay?
Go.
We're gonna assume that it is shaped like a cylinder because the math is easy. And most spaceships sort of look like a cylinder, according to NASA anyways. And let's assume that the inside wall of this guy right here is what? Is 0.25 meters thick?
Yes.
And the radius is what, 4 meters?
Yes.
And that the height is 25 meters?
Yeah.
Okay? Great. And unfortunately, I don't have another color. Oh, wait.
Oh, there's yellow here.
Yellow.
That helps.
It looks like a highlighter more than a...
Right.
Ah, it works. Okay.
Orange.
So, but see, what I'm saying, my head didn't ask for an extra point because of that.
Mm-mm. I just assumed it was given.
Okay, fine. Just want you to know, you hear my feelings, just so you know. I hope it makes you feel better.
Such a quasi.
If I were you, honestly, I always just.
Okay, 25 degrees inside and mine's 183, right? I'm not looking at the
Yes.
sheet. Okay, mine's 183 outside, okay. So we know that there's going to be a heat transfer from hot to cold. This is something we learned. And heat transfer from hot to cold, we know the process in this case is going to be through conduction. Right? It could also be through radiation because it could emit, and that's probably one of the ways in which it would actually work, but there's a transfer. So let's assume it's conduction for now. And in conduction, we know that the heat's going to transfer per time, right? Amount of heat per time is going to be basically it's the thermal conductivity. So K is the thermal conductivity times the area divided by the thickness times the change in temperature. Okay? So in this case, we want to figure out how much energy we're going to lose per second out to space. Okay? So what it means, I think the K was a 0.012. I'm pretty sure, right? And L was 0.25.
Yes.
And the area, now we have to consider the area as the top area, the bottom area, and the sides. So the top and bottom, of course, are the areas of a circle, so it's pi r squared. So it's 2 pi r squared. Okay? And then the sides is a circle times the height, right? So it's going to be 2 pi r times h. Okay? And then the change in temperature is going to be 208, right? 208. Negative 208 degrees Celsius. So if I look at this, 2 pi r, so I got 2 pi r plus h, right? So I've got 29 times 4, right? 100, right? What is it? 116 times 2 pi, right? So this becomes 0.012, 125 times 116 times 2 pi times 208, whatever this number is. No one has,
I just
you just did it?
no, I just took my calculator. I'm gonna do it.
I don't know if this is right, but I have negative 7,236.
Negative 7,000. Well, negative's okay because we're losing heat, right? So we're losing heat, so it's negative. And 7,000, let's see,
Negative 276.
7,276. Okay, this is joules per second, right? So that means every second we're losing 7,276 joules. I'm gonna think of it like that. So we have to replace that 7,276 joules every second, okay? Now in the ship, apparently the ship is configured with a, what is it, a 13 kilowatt reactor? Is it 13 kilowatts, 13.5?
Yes. 13.
13, okay. So that's how much power is produced by the reactor. And it also says there's some consumers in the spaceship, right? So there's life support, right? What was that, 1 kilowatt?
1 kilowatt.
And then there was, what, control systems,
Uses 2.
2 kilowatts, and then propulsion, what was it, 6.5?
Yes.
Propulsion. And of course, in a real spaceship, there would be others, You have, systems for, experimentation, you have backup systems, and whatnot. So anyways, this is 9.5, so what is that, 3.5? 3.5 kilowatts. Okay? So that's how much, 3,500 watts is what it produces. Watts are joules per second, right? Okay. But we dissipate 7.7276 watts. But the thing is, this is how much watts the reactor has. Now, we have a heating system inside the spaceship, and the heating system, right, has a COP, is it 3?
I have
That
one question.
Yeah.
Why did you subtract all of those?
Because this is how much my reactor produces, but this is a user, this is user, this is a user. So this is a light bulb, this is,
So that's what's left?
so this is the remaining, yeah, this is available.
Okay.
Available power. Okay? So we have a heating and cooling unit, and this heating unit has a COP of 3, which is basically, the COP represents the heat it can generate and the amount of work required to generate it, right? And that ratio is 3. So we can sit there and say that the work, which is equivalent to, so the work, right, is gonna be Q over COP, okay? And the heat we have to basically make up for is this heat right here, right? Loss per second, right? We have to make up for that heat. So that's gonna be our 7276, and the COP is 3. So I don't know how much that is right here. That's 72. What's 2? It's 24, right? 2,400. 2,400. 2,425.3 joules. Okay. So this is how much work is required to produce heat of 7. So it has to do that per second. So therefore, this, you consider this per second, then this represents how much power you're going to need to produce this much heat from your AC. So that's cool, because this is saying that, effectively it's saying it's 25.3 watts, right, is what I need, to keep me from freezing my butt off. And I have available to me 3,500. So we have more than enough power to stay warm. Your sister's not coming at all, you said.
How's videoing it? So that way it'll be on Blackboard later.
Okay, so this is the first, I guess a little more than half the problem.
That's a half a problem.
Yeah, a little more than half the problem, yeah. So this is one of the answers. How much power is required? The question is, do I have enough power to stay warm? And the answer is yes. And this is one of those where you can say yes. And I won't take out points.
Why the yes?
Because the question answers, do you have enough power?
Oh.
I could say, explain to me why you have enough power.
So you have 3.5 available, but it's only using 2,000.
But I'm giving you a free pass.
Okay.
So,
Thank you.
yes. Victoria, I know, right? Okay, the next part of the problem is saying that now we're in the sunlight, and in the sunlight, the heat outside is much higher. So now I'm at, what is it, 220?
Yes.
Outside is 220, but I still want to maintain my 25 degrees Celsius on the inside. So in this case, I'm actually I'm absorbing heat from the outside. It's still a conductivity problem, but now the sign is going to be reversed. So in this case, I have my the heat of my heat. The ship is absorbing, or I'm absorbing the ship. Again, it's going to be AL over delta T. This is going to be 0.012 times 2. What was it? Was it 2 pi last time? Times 116. And the change in temperature this time, right, is going to be 245. And it's positive. And then the thickness is 0.25. So this is the amount of heat we're losing, right?
Why is delta T minus? Like, why is
Here?
it 220, yeah. Wouldn't it be 220 minus 25, so wouldn't it be 195?
Yeah.
No, you're right. It is 195. You're absolutely right. You're absolutely right. Because it's T final minus T initial. You're right. Okay. So this is going to be equal to something. To something, something.
Where did you get 160?
4 plus, the 4 plus 25 is 29. 29 times 4 is 116.
1,705.5.
705. 1,705? Like 705?
At 1,705.5.
Wait. How did you get 7276 here and then 1? Did you forget to divide by the 0.25?
Mm-hmm. I did.
Okay.
So you say units for 0.25, is that meters?
Yeah.
Okay.
Yeah, it's half a meter thick, so it's M.
I got 9.8.
You got 9.8?
Yeah.
I got 6,800.
Is that
6,822.
Point 012, yeah, 0.012 is what the K is given in the question.
I got 6,822.0.
Okay.
That's 1/6.
Yeah.
Oh, no, that's 1/6.
6,000.
6822.
6822?
I thought that was 1/6.
0.03.
Okay.
Is that good?
Just for a second. Oh, it's fine. I mean, it sounds, like if you got 72 here, then it makes sense. Because this was 208, that's 195, so it should be reasonably close. Okay, but this one's positive now, right? So again, same COP, we have the same COP, so we're gonna, the amount of work required to give me that much heat, this heat right here, right, is gonna be the 6822.03 divided by 3 is going to equal
2,274.01.
okay, joules. And if I look at the reactor, I say, now this is joules per second, so basically in watts. So the amount of energy I need, or power I need, right? It's going to be 2274.01 watts. And I have 3,500 available. So again, we're good. We will not cook inside the rocket ship. If you guys really want to take this seriously, you got to figure out how do you end up getting rid of heat. So it's easy to generate heat inside of a space station because you just like use something with a resistor on it, give it some current, it'll generate heat. But how do you get rid of the heat? In most AC systems, you need to dump it somewhere. But the place you want to dump it is actually hotter than the place you're at. So how do you get rid of it?
You act like a refrigerator, you do work, you do everything.
Well, you're already doing work just to convert the air from a warm temperature to a cool temperature. But I'm saying is now you got that work you did, the output, even in your refrigerator, the output's hot air. So where are you gonna put that hot air?
Dump it in space.
That's a good question.
So then you got another problem then.
You'll run out of air.
Well, you just
Exactly.
You just
Huh?
live the way, you know.
You do what?
You just live the way it is. Like,
At 220 degrees Celsius.
yeah, I mean,
So you do understand that water boils at 100 degrees.
yes, I understand very well.
You'd be dead.
Yeah, well, I mean, what else can you do?
Actually, this is a real problem in space, guys. Heating is much easier than cooling in space.
So what do you do to get rid of
They
it?
have really high, they have a lot of insulation, so they minimize. So instead of having the 0.012, they have a lot
Do
more
you just like turn
insulation.
everything off or not make anything?
Well, think about it. Every electronic on a spaceship generates heat. You know, it's really hard to get rid of that heat.
What did they do?
Huh?
How do they actually get rid of it?
Well, keep in mind, they also have a very limited amount of power. I mean, none of them really work on nuclear reactors. So they don't have any, I mean, the Russians were pushing it in the mirror, but US and Europe and Japan won't put nuclear reactors in the space station. So they actually have a limited power. They use solar cells to generate the majority of their regular power. And they use low ohmic heating and everything else for their, and all the electronics are 70s level. I don't know if you know this or not, in the International Space Station today, the electronics they have is like late 70s, early 80s vintage boards and stuff, which use a lot of power for very little processing. So yeah, it's a real problem. They don't fix it, they just skirt around it, right? You know,
Yep, that's all until we start destroying the earth, right?
until we start destroying Earth.
Or until, you're right, until we start destroying the earth until the point where it's almost no longer habitable, right?
I don't understand the connection.
Like, as in, like, we're probably not gonna update that space technology for a while.
Until it crashes in the Earth, we'll never update that space technology. It's gonna burn in the atmosphere. What's up?
Do we have planets that are cold, like colder than the space?
Do we have planets?
We're in space.
Okay, so I can give you an example. The surface temperature on Pluto, if you want to consider that a planet, is something like minus 290 degrees.
Alright, so if the spaceship was close to Pluto, could they dump the heat over there?
Yeah, but that means you'd have to be stuck next to Pluto just to keep yourself cool. It doesn't really make a lot of sense. And the other issue with that is that they generate most of their power from solar. Out at Pluto, there's not much light, so they're basically screwed.
Okay, there we go.
Yeah. Okay. So we're good? I can erase?
No.
I can? Good.
Kilograms of ice at -55. How much energy would it require to convert all of it into water? How much energy would it require to convert all of it into the ice into steam?
Okay, so we have ice at, this represents an at sign. Okay, Yogi's not here, of course, right? It's minus 155 degrees Celsius. We want to convert this to water. Right, it does say water, right?
Yes.
At 0 degrees Celsius. That's part one, and then part two, then it wants to say in part two, it's going to say I want to convert it to steam, right? At 125 degrees Celsius.
Yes.
Okay, so this is part A. Okay. The other part's part B. So step one in this case, to basically to melt the ice, warm it up and melt the ice, is we're going to warm the ice, right? So we have ice at minus 155 degrees Celsius, and we want to warm it to ice at 0 degrees Celsius. So whenever we're warming a material that's in the same phase, we use a regular equation, the Q equals mc delta T, and basically it's related to the specific heat capacity of that material. So we have C of ice equals 2.01, C of liquid water equals 4.184 or 4.86, and then C of steam equals 2.1. Okay, 2.01. Okay. So in this case, now this is 2.01 joules per gram. So that means we have to convert this into grams, so we're in the right unit. So it's going to be 5,000 grams. It's 2.01 joules per gram, degrees Celsius, right? Times the change in temperature. This is going from, minus 155 there to 0, so it's 100, so it has changed by 155 degrees. Okay? That's cold ice, by the way.
It's 1,557,700. 1,557,50.
Okay, now the next step, right, step 2 is going to be ice, converting ice, which is at 0 degrees Celsius, and we're going to convert that to liquid water, right, at 0 degrees Celsius. So what do we call that when we go from a solid to a liquid?
Melting.
We call it a change of phase, right? So in change of phase, now in this case, the phase we're doing is from a solid to a liquid, so we're going to use the latent heat of fusion. Okay, fusion refers to either melting or freezing, because we're using energy that's associated with the fusing or the defusing of the material. So we have 5,000 grams times now latent heat of fusion for water, right? I think it's 80 calories per gram.
Yes.
Okay, so this is 80 calories per gram. Now, this is in joules and others in joules, so I guess we're better off just getting everything in terms of joules. So to convert joules, I need 4.186 joules per calorie. Okay, and that's going to give me now, it's going to get rid of my calories, and it's going to give me joules. thickness, 1,600,000 something,
1674400.
like that. Yeah. Are you just looking at from last time or what?
Last time.
Oh, you have a lot of faith in your friends.
I just that's a number.
Why don't we convert grams to kilograms? If we're measuring in joules, and you were measuring kilograms.
Whoa, why would I, you're asking me why don't I convert grams to kilograms? But we were already in kilograms, we converted from kilograms to grams. So why do we wanna go backwards?
I mean, why do we convert from kilograms to grams?
Because we're using this guy. This guy here is in joules per gram degree Celsius. So what you really want to do is it's the most convenient thing to do is choose the unit that the specific heat capacity is in. If it's in kilograms, then use kilograms. If it's in grams, then use grams. That's the easiest, safest way to do it. And it's easy for you to convert, 5 kilograms to 5,000 grams, right? Okay. Now you could have done it in kilograms, but that means you have to convert this now as well. Yeah? Okay, so right now we have melted the ice. Okay, and we're at 0 degrees Celsius. So we've completed part A. So if we add these two together, we get the answer for part A. Okay, whatever that number is,
That's
3,200,000.
3232150.
Okay, that's the answer to A. Then we want to continue now to go to steam, and steam at 125 degrees. To get the steam now, we have to warm the water, we have to convert the water to steam, and then we have to warm the steam. So we still have some steps left, right? So we start with step 3. This is taking water, right? At 0 degrees Celsius. And we're converting this, or warming this to water, right? At 100 degrees Celsius. Basically, we're warming up the water. And when we're warming something that's in the same phase, again, we use this formula here. It's going to be Q equals MC delta T. And in this case, again, the mass is 5,000 grams times the C, specific capacity of water, is 4.186. 6, and this is joules per gram degree C. And then change in temperature. So we went from 0 degrees to 100 degrees, so the change in temperature was 100 degrees. Okay, degrees Celsius, and that's going to give us some number.
2,000.
2 million.
2,093,000.
93,000. Okay. Now step 4, we're going to take that water and we got to now convert it to steam, right? So we have water, right, at 100 degrees Celsius, and now we're going to convert that to steam, right, at 100 degrees Celsius. Now, some of you guys will make mistakes and skip some of these steps because you figure, okay, once I got it hot water, I can just go to straight hot steam and not worry about change of phase or once I got, so I go straight to 125, steps like that. You want to be careful. Always identify where it is you're converting, you're doing conversions of phase, right? In this case, you're doing the change of phase, and it's going to be the latent heat of vaporization, okay? So now it's between, condensation or vaporization of a gas or a liquid. That latent heat is different, of course, than it is for fusion, which is the freezing. Again, this is 5,000 grams times, now latent heat, I think it's 540 calories for water per gram. And again, we're going to multiply by 4.186 joules per calorie. I think is this nice, almost like 11 million something.
11,302,200.
Okay, so you can see there's a lot of energy stored in steam. Of course, you're not going to douse yourself in 5 kilograms of steam, though. That's tough, but it's still a lot of energy. Okay, the last step, and now that we have steam, we have to warm the steam up. So step 5 is we take our steam, right, which is at 100 degrees Celsius, and we heat it up, right, to steam at 125 degrees Celsius. So we're in the same phase, so that means that the equation we're going to use is MC delta T. Okay, again, this is 5,000 grams times specific capacity of steam is 2.01 joules per gram degree C times the change in temperature. And this change in temperature is just 25 degrees. So it's like 250,000. Or is it 252?
251250.
Okay. So now you're gonna to get the total answer. The question's asking, basically asking how much energy is required to turn this all into into steam at 125. So basically you're gonna add all these together, right? Plus A plus this, and this, and that's gonna give you the answer for B. Okay. Which is like 16 million some odd times.
Wait, plus A?
Yeah, because you need to go from here all the way to there.
So you're adding to all the 5 steps?
Yes, you're adding all 5 steps together. It's basically 2 questions in one. So it's 16 million, what is it, 2, 3,
16878600.
there you go. Easy peasy lemon squeezy.
Each wing has an area of 40 meters squared. While flying at 239 kilometers per hour in level flight, the plane keeps climbing with an acceleration of 2 meters per second squared. And the mass of the plane is 800 kilograms. What is the pressure difference on the wings of the plane and the heat? You double the speed, how much would the pressure difference change?
Okay, so there's a rigorous way and a hand-waving way. I think we're better off now, since we've already seen this once, to do a little bit more of the rigorous way to do it. So when we're looking at this, air has to go from this point here to this point here in a certain amount of time. Time it takes the air to go is delta T. And the air and the top and bottom have to both arrive at the same location in the bottom in that same delta T. Now right away you'll notice that if the air is moving at speed V, I'll call this the V air, right? Is moving like this, that means this distance over time is literally the V air. Or what we can call is V lower. V under the wing, you guys want to call it under and above, or lower and upper?
Lower and upper is fine.
Okay. So here, that means that this one here is going to be V upper, right? But if I look at it, it's just D over delta T, which is my VL plus delta. Okay, so that basically equals VL plus delta V. So the air on top is moving a little faster than the air on the bottom. Okay? Meaning that because even though it's going from this point and this point, getting at the same time, it has to cover a longer distance. So that means its actual speed is a little faster. Now what we learned from Bernoulli's equation in general, right, was that the speed squared plus p, if there's no change in height, is equal to constant. So we said that if our speed increases, our pressure decreases. If our speed decreases, our pressure increases. What's up, man?
You said VL plus delta V. You mean delta D?
No, it's delta D over time is
I got you.
change in distance over change in time is
Mhm.
speed, right?
Mm-hmm.
So it's a little bit more speed. This is V plus a little bit more.
Yep.
So what is delta V?
Delta V is a some
Delta V,
small
delta
amount.
D.
Like if this is 239, this will be 255 or something, or 260. Okay? It means that because I had to cover more distance at the same amount of time, it means it's moving slightly faster. So this is the relationship we learned from Bernoulli. So if we look at it in terms of the upper and lower, we can say 1/2 rho V lower squared plus the pressure lower equals 1/2 rho V upper squared plus the pressure upper. Now we can see that the V upper is more than V lower, So we can bring this guy over like that and this guy over like that, right? So that means we're left with P lower minus P upper, right? Equals 1/2 rho V upper squared minus V lower squared. All I did was move these around in this way. Now, we said the lower the speed, the higher the pressure, and the higher the speed, the lower the pressure. So that means that the pressure on the bottom is greater than the pressure on top. Now, what did we learn? What did we learn when we had an interface where pressure A and pressure B cross this interface, right? If there's an imbalance, what's going to happen? They're going to accelerate it. It's just a difference in forces. It seems like exactly like the difference in forces, okay? So if there's a difference in pressure, it's going to accelerate. It's going to move. In this case, it's going to lift. So this is our delta P, okay? Or a pressure difference across the wing. And here, 1/2 rho V upper we have is actually V lower plus delta V, right? Squared minus V lower squared. And if I expand this out, if I do FOIL for this guy and then cancel everything out, my final form ends up being 1/2. My final form ends up being 2 delta V is VL plus delta V squared. That ends up being my final form if I expand this out, because the VL squared is
What
canceled out.
about VL squared?
I have VL squared minus VL squared.
Oh, okay.
Okay, so this right here represents formal pressure difference across the wing. Okay, so this is something you keep on your hip pocket for the moment, and it's based on the breakdown of the problem, okay? Which is good. Now we know if we start playing with the speed, right, or start playing with the pressure, we can figure out the relationship between them. Okay, now to answer specifically question 1 of the problem, it says what? It says what's the pressure? It says what's the pressure difference across the wing, right? So right now we don't know delta V because we didn't say anything about the geometry of the wing. So from this part we can't figure out what the pressure difference of the wing is because we don't have enough information. But we do have enough information based on the mechanics of what's happening to the wing, right? So we know the definition of pressure difference of the wing is literally the net force, right? The net force over the area, okay? And this area then represents all the wings, like not just the one wing, but both wings. Right? And this net force, of course, is mass, according to you, is mass times acceleration, or twice the area of the wing. Okay? That's the total area, because we have 2 wings in a plane unless you're a blended body. Okay, so we know everything here, right? We know the mass, we know the acceleration, we know the area, so we're in good shape, right? So we have 800 times 2 divided by 2 times 40, right? 2's, this 20 Pascal. So right now we know that the lift that's being accommodated by this air is 20 pascals. Now 20 pascals is nothing, guys. I mean, think about it. We're standing in 101,300 pascals on our skin right now. 14 pounds per square inch, that's a lot. And I got a lift of an 800 kilogram thing is by just 20 pascals, nothing. But that tells you even a little bit of force difference can do a lot. And by the way, is that right? Did we actually do this right? And I show you guys like a curveball. This is the amount of lift in the wing, but is that even enough to lift the thing against gravity?
If that's acting this way.
This is just one way,
I mean, this is the net acceleration,
right?
right? So in reality, the lift has to be higher. You agree, right? Okay. Well, we'll leave we'll leave gravity out of it for now, so I'll throw you a curveball. So this answers the first part.
Is the gravity part gonna show up in Physics 202?
No?
No.
No, if you want to do it rigorously, now is the time, but we're not going to do it.
No. I
202 is electrodynamics, electrostatics. The math in 202 is really hard. I have to figure out how I can do calculus based off without having you guys required to know calculus. This is going to be tricky. I can do 232 no problem because they're calculus students. So, but doing this for you guys is, and it's not 102, which is basically just conceptual. So you guys are in a sort of a gray zone. So I'm worried I'll push you too hard.
Should we divide the 20 Pascal by 2?
Why?
Since we're analyzing one wing.
we're analyzing both wings. Twice, 2 times the wing. The area of one wing, we use both wings.
What about the delta E?
This right here is just representing the, okay, this just represents the pressure difference across a wing. Yeah, this is a wing. True. But the pressure difference across one wing is gonna be the same pressure difference across the other wing. Right? If we're talking about the total pressure, okay.
So if you, the faster you go, like the more lift you have?
Absolutely. That's what this says. If you go faster, right, what happens? If you go faster, this delta T gets bigger, right?
Yeah.
So let's say you're going twice as fast. If I go twice as fast, it's delta, in other words, if I go twice as fast, that means my delta T is half as big, right?
Yeah.
But that's half as big flips it up, it means this is times 2. And this is times 2, right? So I'm going twice as fast. Well, if I go twice as fast here, this is 2 times 2 is 4, and 2 squared is 4. So that means my pressure difference is 4 times as big. If my pressure difference is 4 times as big, then my lift is gonna be 4 times. You got that?
Yeah.
Okay, so the next thing it says, if I double my speed, and this is basically the story. So doubling the speed, or tripling the speed, or quadrupling the speed, or 30% increase or whatever, is basically just changing these speeds, right? So it doesn't matter. If I double my speed, this is gonna get bigger, and this delta is also gonna get bigger, because the air has to move at a fixed rate across things. So if I double it, this gets twice as big, and this gets twice as big. And this squares twice squared, right? So that's 4. So if I double it, I got a 4 factor here, 4 factor here, which I can pull out. So it becomes 4 times this original. So it becomes 4 times the, do you want me to do the actual algebra? Okay, so this is, I'll call this my 0, my initial, right? 0, 0, 0, okay? And let's say we're gonna double the speed. We wanna know what the pressure difference is when we double the speed. So now this is gonna be 2 times twice delta V0, because we just doubled that, right? Times twice VL, 0, because we just doubled that, plus twice delta V0 squared. Just doubled the speed, right? So now, if we look at this, we have the 1/2 rho. This 2 and 2 here is a 4, so I got a 4 here times 2 delta V0 VL0. You see what I did? I took these 2 and brought it here. And then here, I got 2 times 2 is 4 times delta V0 squared. Okay, and I have a factor of 4 I can pull out. So that means I get 4 times 1/2 rho of my 2 delta V0 VL0 plus delta V0 squared. And that means that this delta P is, but this right here is exactly this guy. So that means I have 4 times delta V0. So you don't have to do the algebra, but I'm saying if you did it, you can see it. And it's the same for 3 or 4 or a half or a quarter, right? If I'm going half as fast, then this would be a half here, a half here, a half there, and so on. And you do the same kind of algebra. So the number doesn't change. So you see now that my pressure difference is going to be 4 times bigger. If my pressure difference is 4 times bigger, my area doesn't change, my mass doesn't change, that's going to translate into my acceleration being twice as big, or 4 times as big, sorry. You see it? Okay. So, this is a little harder than it was in the last test, but it's only because you guys are actually doing the algebra. Okay? And then was it number 4?
It's a car jack.
Making a cylinder, right? It's got a plate here, with some area. Okay, and you have your car. Okay, and this guy's what, 4,900 newtons?
Yep.
Okay, it weighs 4,900 newtons. So this is, this right here is V initial, E initial, T initial at this point, right? And then this height from here to here, right, it was a 0.25 meters. And what's the radius?
0.25.
Also 0.25 meters, okay? So, what do we know? If this guy's holding up, if this guy's not moving and it's got a 4,900 pound weight on it. What do we know about the pressure pushing down or this internal pressure? We know that the internal pressure, or the initial pressure to start off with, is going to be what? It's going to be the pressure created by this weight in this area, right? Which is going to be the weight of the car. So it's the weight of the car, right? Over the area of the piston here. That's part of it, plus 1 atmosphere, right? That's your initial pressure pushing down in this guy. And if it's not moving, that means this pressure has to equal the outside pressure, okay? So that initial pressure is going to be the 4,900 over this area here is pi times 0.25 squared plus 1 atmosphere, which is 101,300,000 Pascal. Okay? So whatever that number ends up being. I'm not even kidding. You could take a little heating element for, that heats tea or whatever, and it'll work. If you got a good seal on the piston and lubricated, just get a metal cylinder, about 1 meter long, seal it on the bottom with cement and rubber on the bottom, and then you get a piston seal for it made. Weld on some attachment points for your lift, and you're good to go. You know how much a lift in your garage costs? $10,000–$15,000. Yeah. So, I'm giving you a $200 solution.
What material should be made out of again?
Huh?
Material should be made out of again?
What should what be made out of?
The material.
You're better off with steel, because it's easier to find a container that will fit inside the seal. It makes a nice good seal on it. Steel, and also it doesn't corrode real well. Okay, so what did this end up being?
126,255.
126,255 Pascal. Okay.
.4951. What? 550.
Okay. Is there a reason why you went to so many decimal places? And no one ever explained you sig figs to you?
They did.
Okay.
Well, you did say the other class that if we rounded drastic, not drastic.
Okay, I said when you do your last, the only time you should round it all is in the last calculation. Like when you're done the calculation and then you just round to the appropriate.
Right, but .4951 is actually more accurate than .5.
Well, it depends, right? And what your measurement is it exact? I mean, here in this case we have a .25. So theoretically you could go to 2 decimal places. If you want to stick with sig figs.
If you know you have that much pressure, how would you find how thick the steel needs to be? Like a thick, so it doesn't break.
Oh, yeah, so that's exactly right. So basically steel has a stress, it's called a bulk modulus. We only mentioned it lightly in class, but usually about a 1/4 inch thick steel, 20 gauge, 24 gauge is more than enough to handle this kind of pressure. This isn't really that high. Remember, we've got 100,000 on our skin. So think about it for a minute. That's not that high, right?
Yeah.
Wait,
This is only 20,000 more. It's 20% more, huh?
Is aluminum weaker in heat than metal, steel?
Aluminum has a higher melting point than steel does. So aluminum's also a lot lighter. But aluminum's also more brittle than steel. Huh?
Carbon steel.
High carbon steel? High carbon steel is brittle. Steel is without, you know what steel is, right?
It's just iron more oxygen.
Iron, oxygen, carbon.
Yeah.
But iron is actually really flexible. It's malleable. Okay, so this is a part A. I guess this is the first answer. Okay. And the second part saying is now we want to. How much do we have to increase the temperature to make this guy go up an additional meter, right? So I want this to go 1 meter more up in the air.
If the temperature is 25. The ambient, does that matter?
Yes. T initial is 25, right? Okay, so in this bad boy, we're going to use that formula we learned in class about the relationship over 273. Okay? So we're going to increase the volume. Now the trick to this one is We do know the volume, but we don't have to worry about it because the area doesn't change, only the height changes, right? So this is gonna be the area times the final height equals the area times the initial height as 1 plus change in temperature over 273, okay? So we see here the areas go away, so therefore we know the final height. The final height is gonna be a meter above this, so the final height is gonna be 125, 1.25. The initial height was 0.25, right? This is gonna be plus 1, and we're gonna increase the temperature something, right? So T final will be T final minus 25 degrees Celsius over 273. Okay? So if I divide 125 by a quarter, it's like multiplying by 4, so this is 5 equals 1 plus T final minus 25 over 273, right? And I can bring this over as 4, so I have 4 times 273 equals T final minus 25. That means T final. So if I just need the change in temperature or I need the final temperature, that's open for discussion. If I want the change in temperature, I don't need to include the 25. If I need the final temperature, I need to include the 25. So however you guys feel more comfortable doing it. 450 to 1,000 is 23, 80, 92, right? 2 minus 25, right? 67. That would be the final temperature, I guess. But the change in temperature would be 1,092. You guys appreciate the difference? No? And then there's one more thing after this, or no? Oh, yes.
Air breaks down at 400 degrees Celsius would be the maximum height that could be lifted.
Okay, so we're gonna go back to this guy again, which is the H final equals H initial 1 plus. Now this is gonna be 400 degrees. Air breaks down at 400, you said?
Yes.
273. Okay, so what's the maximum height? Well, we're starting at 25, or 0.25, right? Okay, and this is gonna be 273 plus 375 divided by 273. Okay, and you're gonna go 658 over 273. Okay, so 0.59 meters. So that tells you that you can only get it up a little more than half a meter when you lift the car up. If air indeed breaks down at 400 degrees, I'm not sure that it does, I have to look that up. I know it's closer to like 700 or something. When the air actually breaks down. Dielectric breakdown is really high. Okay, we're good? Grams of copper, right? And what is the mole mass, the atomic mass was what, 63.5?
Yep.
Okay, so first thing we want to do is find the number of moles. The number of moles here is going to be the mass divided by that molar mass or atomic mass, which is going to be the 4.8 over 63.5. And then from there, we can find the total number of atoms. It's gonna be Avogadro's number times the number of moles. So in this case, what is it, 6.02, 1 point,
Yeah,
10 to
6.02
23.
times 10 to 20.
times 4.4863. I don't know what, I don't remember what this ratio is.
4.55 times 10 to 22.
No, what's this ratio? You're just writing the answer down?
They're grams. Oh, the rate.
Okay, fine. The total number
Well, I mean,
is 4.22.
it's 5.5.
4.55
Yeah.
times 10 to 22 atoms, right? Okay, I'll just write this just in case you guys take a picture later and you go, how did you get that? Okay, all right, good?
Mhm.
Okay. The problem with doing multiple choice, you're just gonna remember the answer, not the question. Mm-hmm.
I know.
It's 0.07.
0.07?
Yeah. 0.07559.
Okay, that's all.
Why
So-
did you need the ratio?
What'd you say? What'd you?
Why did you need the ratio?
Because I need it here. I thought we were just gonna, so I could put it on. But it's all right. I mean, you guys just use a calculator. Okay, number 2.
How many calories are required to melt 30 grams of copper at its melting point?
Okay, 30 grams of copper. So I think the latent heat of fusion for copper is what? Is
30.
is 32, right? 32 calories per gram? Which is not very much when you think about it. You know, so that means that the Q is MLF, which is 960 calories.
Which of the following expands when the temperature is lowered?
So, basically what I wanted you guys to learn from class is that almost everything increases in volume as you increase this temperature. Pretty much everything does that. Everything natural, and even most unnatural things. There's a few man-made things that don't do it, and then there's one very specific natural thing that does do it, and that's water. So, 4 degrees, 0 degrees Celsius. So water is the only one that from 4 degrees to 0 degrees Celsius, it actually, its volume increases. Okay? And that's it.
Can you go through the explanation one more time?
I should have been what?
Huh? What'd you say?
I said, most natural things occur in nature increase in volume as you increase the temperature.
Okay.
With the exception of water. Water is the only one that increases in volume as you decrease the temperature from 4 degrees Celsius to 0 degrees Celsius.
Okay.
And this is exactly the reason why you have to, you know, leave a tap running
Mhm.
or drain a pipe when it's starting to freeze, or else you're gonna have pipes burst.
I was thinking about that the other day. My mom got a ring, and like, the jeweler was like, "Oh, your hands are kind of warm, so that's why it's kind of not fitting well right now."
So when her hands get cold, her hands are gonna shrink and her thing's gonna slide off.
Yep.
And then she's gonna lose it.
And then it's
And
a lot of
then
money
game
wasted.
on,
Uh huh.
right?
End of the world.
Yep, your mom will be like,
If there's such things as adjustable wedding rings.
adjustable wedding rings?
Mm-hmm. Like, you
Yeah,
know,
it's called
like-
divorce. No, there's no, I mean, not unless you guys got one of those like twisty tie things or something.
Like, I know there's like the.
You can buy those rubber pieces that
Right,
you
yeah.
insert,
No.
but that's not the wedding ring, it's adjustable, your plate.
Sorry for interrupting, by the way.
Okay, no problem. I had to say something. Just a wedding ring, yes. It's a removable ring, you get divorced.
Technically, you can call those things a wedding ring.
Okay, I'm waiting.
Do I do that like reading every single question?
Well, no one else is volunteering.
Oh, I think. Which one?
Oh,
Suppose the temperature of the input reservoir in a heat engine doesn't change. As the temperature of the cold reservoir increases, the efficiency of the engine.
Okay, so if these guys do not change, they're constant, they're 5, whatever. and this guy starts to increase, that means this difference is gonna get smaller, which means this ratio is smaller, which means this number gets smaller.
Yeah.
Okay? In other words, the closer the temperatures are between the hot and cold reservoir, the lower the efficiency, right? And then if you, on the other hand, you say, I decrease the temperature, in other words, I spread the temperature, I made a wider range between the hot and cold, then my efficiency is gonna increase. Good.
Joules is required to warm up 50 kilograms of copper from 20 Celsius to 94 Celsius.
Okay, so, the C of copper is, 397 joules per kilogram. Okay, so you notice that's in kilograms, so you wanna keep this in kilograms, right? So you have Q equals M C delta T. So you have 50 times 397. And what was the temperature change?
74.
So it's what? 94 minus 20 and whatever?
Yeah.
Okay. So that means Q equals whatever. 1,400,000, 14 million, I don't know.
Yeah,
Yeah,
one
that's-
four
that's
six
it.
eight.
14468?
No, 1468.
1468
Yeah, 900 joules.
902?
0. No, joules. 1 minute.
Oh, wait, it's, oh, never mind. Yeah, I miscalculated.
Efficiency of an engine that absorbs heat.
I'll
from-
probably get rid of this one, it's too easy.
Yeah. No.
Get rid of
No,
it,
no,
like
no,
just
no.
remove it, like completely and not
And replace it with an even better one that you'll enjoy
No.
even more.
Yeah, it's in like
Don't do it.
order.
Then keep
Kill
it.
it.
I thought you were just gonna delete the question forever and not replace it.
So I give you less questions, so that means each question is worth more, and if you make a mistake, you lose even more for it.
Mm. Or you can give us 11 and then say you can choose 10 to do. Mm.
Although if you keep
Oh, true.
It's not a bad idea, right?
You know what I noticed? I noticed, especially in my other class, is that if I do a review session and I don't change, you know, if I keep the
Maybe it's wrong 'cause you think that you're gonna switch it.
Ms. Roy, you are
Yeah,
a
like
wealthy
what-
woman. I take cash and credit. I'll even take diamonds if you got them. I'll find someone to pawn them off. Don't worry.
Mhm.
How do I accept credit? It's a little app on your phone. You still have to plug it in.
Oh, the square.
You do it? Okay.
200 joules of heat are added to a system that performs 160 joules of work.
So we gave it 200 and we took from it 160. That means we're left with 40 joules of an increase in internal energy. So the increase in internal energy was 40 joules. Now, this is also very, very easy. I should incorporate this into another problem. That's what I should do.
No, the
No, you
short
should
answer
not.
is an hour long.
Short answers take a while.
Yeah, you
So,
should do it.
just.
Just chill?
Yeah.
Still? Okay.
Mercy, it's
Mercy.
Determine the kinetic energy of a gas at temperature 90 degrees Celsius, whose constituents are molecular oxygen. The atomic number for oxygen is 8 and the atomic mass is 16. 1 U equals 1.66 times 10 to negative 27.
So, in class, I don't know if you guys remember this, we did 1/2 mv squared kinetic energy was equal to 3/2 kT, is that right? Anybody remember that?
Never did discuss that.
We never discussed it in dynamic pressure in class. You didn't come to that class, remember?
Oh, I don't remember doing that.
Is that last week or this? Yeah.
It was,
Oh, okay, Monday, this Monday, yeah, I didn't, okay.
Anyways, so this is a cheat. I'm actually cheating for you. So instead of having to deal with, remember there was a formula, one formula I gave you which said V equals blah 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 square root of whatever?
Yeah.
And then from there you have to plug in this guy, and from there you got the kinetic energy. But instead you can just, hey, you can just do this,
There, TKT.
right? Well, there it is. So there we know. So the kinetic energy is equal to 3/2 times Boltzmann constant, and we got it?
1.38.
Right, times temperature, what is it, 363
Yeah.
Kelvin? Right?
Yeah.
There you go.
7.51.
Is it 23 or negative 23?
Negative. It's 7.51 times 10 to negative 21 joules.
Wow, so much easier.
So much harder. 2 kilometers an hour.
Okay, and
In a 500 kilogram car.
The distance is 50 meters.
50? Okay. So, and the braking force is what, 5,000?
4,000.
4,000? Have any of you guys sat down and tried to figure out what the braking force in your car is yet?
How would you do it?
Why?
How would you do that?
Yeah.
Seriously?
No.
Oh my God, no. I'm
No,
gonna
no.
start investigating your grade now. Okay, the easiest
No.
way, the easiest way to do
Okay.
it,
I got it. Go a certain
Okay,
speed.
got it.
the easiest
Alright,
way
go
to do
ahead.
it is
Okay, got
basically you put a cone on the ground, on the road, right?
Okay, and then.
And you basically, as you come up at a certain speed, you slam on your brakes to that point,
Okay.
and then you get out of your car where you stopped and you measure the distance to that
Yeah.
cone. And with that distance, you know everything.
But it has ABS brake, right? So-
It does. So it's, but still, it's.
Wait, how does that, like, that's, like, stops and then let's go?
1 second.
Didn't they teach us when we were getting the license, like, there was
No,
this
they
thing
teach you,
about the 3-second law?
Yeah, if you're going a certain speed, you wanna be 3 seconds behind the following car, yeah.
Oh, yeah, that's what
ABS is the way it works is instead of just slamming on your brakes and it grabs the tire and locks
Yeah.
up, which means you lose traction and you start skidding everywhere.
And then.
ABS basically is a little computer that makes it go like this instead.
Oh.
So it prevents it from locking up, so it maintains connection to the road. And
Oh.
see, leaves it, it keeps you from slipping. So as this guy now, we know the force. So if we know the force, right, the net force is this guy. So the force equals mass times acceleration. So it means your acceleration or deceleration in this case, because it's a negative 4,000, right? Is going to be minus 4,000 divided by your mass, which is 500. Okay, so it's minus 8 meters per second squared. And then we said that V final equals V initial plus AT is a formula. V final, of course, is equal to 0 because you're stopping the car, right? So that means you have V0, and V0 is 115.2 kilometers per hour. We're going to divide it by 3.6, so I think that equals 32 meters per second minus 8 times time. And now since this equals 0, we can solve for the time. So the time equals 4 seconds. Okay? So now that we know the time, we know the distance. Because we know that change in distance equals the V0 times time plus 1/2 AT squared. So that's 32 times 4 minus 1/2 8 times 4 squared. 8 times 4 is 32 times 4, 1/2. 8 times 4 is 32 times 4 is, so it's this minus half of itself. So the change in distance then is going to be 1/2 32 times 4, right? 16 times 4 is 64 meters. Therefore, you're going to hit your roadkill. You know, there are people in the South that actually collect roadkill and they eat it.
That's what we're referring to.
Yeah.
Why do you say it tastes bad if it has like ethanol?
Oh, okay. So this is R0. This is I0. This is omega 0. And then she pulls her arms in. Now it's R final. I final. Okay, omega final. And since there's no external forces acting on her, the consequence is that the angular momentum before and after has to be conserved. So the angular momentum before is I0 omega 0. And the angular momentum after is I final omega final. And by the way, if you guys want to think about making money,
Yeah.
you can get, for a good sized tuna, you can get $100,000, up to $100,000 for it.
For
You know,
what?
fitting out of the med. $100,000 for a good sized tuna. Japan pays that much and more for them. So one of my projects, I'm gonna make a fish farm out in the middle of the ocean. Cause I tell you, for $100,000 a fish, it is. Yeah, it's sort of funny. I used to spear those by myself when I was a kid, you know? So L0 equals L final, because angular momentum is conserved, right? So that means that I0 omega 0 equals I final omega final. If you guys like the water, you're more than welcome to join me.
I'll join you.
Right?
It has to be good quality fish though.
Well, ocean bred yellowfin tuna is a
And
pretty
you have
good.
to have the right fat constitution.
If you're bred up in the med in the same environment as all the others, it's probably pretty good.
If you sell it to me, I'll give you $50.
$50. Going once, going twice.
For what, a fish?
$50.02.
You guys think I'm crazy, but a large tuna will catch $100,000, and I'm totally serious. You guys done?
Yes,
You good?
yes, we are.
So let's stop giving that boy so much attention.
So tomorrow, 12:15?
12:15?
Or 12?
What? Wait, what? You guys aren't coming to the review tomorrow?
Which review? I have class, I have calculus
Until what time?
until 12:15. Well, until 12:30, Mom.
Okay.
There's one at 5.
Well, the Bob sisters as well, they're talking about taking the test tomorrow at 12 at my house.
Yeah, that's what we will do.
Yeah. But there's actually a review at 10 tomorrow at my house. You guys are in class.
I'm not sure if we will miss the class, but we'll see. Because it's my last class, she's doing everything also. We'll be fine though.
What her class is on?
Priorities. Which one's the
'Cause
priority?
Are you gonna boost the video?
Mm-hmm.
We'll see that too. We'll be fine. Thank you so much. Thank you.
Take care.
I'll give you $100,001.
Was it 2.38, 2.36, 35? 2.816?
4 divided by 1.25 times 0.88.
Is 2.416?
No, it's 2.25.
Oh, yeah,
Can do
2.816.
that.
16, okay, so 8.2, I guess.
Yeah.
Okay, so that's it. We done, we did.
No, it's 2.346.
Okay, you know what, whatever, just.
No, 0.88 times 4 divided by 1.5. Oh, wait, what?
Is it 1.5 or 1.25?
1.5.
Okay, well, that's my problem, there you go.
Okay.
So now it's
Change
what?
that number.
2.35. We're done.
Okay,
Bam.
so Corey, what problem did you come in on?